It's my pleasure to introduce the next speaker, Andreas Hoecker. One of the most important influences on SLAC over its 50-year lifetime has been SLAC's membership in what one might call the global sorority of electron laboratories. So these include KK, DAISY, I'm sure Professor Dosch will tell us more about that this evening, Frascati, and Novosibirsk. I'm myself a product of one of those laboratories, Cornell. And the speaker now is a product of another one, the Linear Accelerator Laboratory at Orsay. Andreas Hoecker is actually a PhD student of one of our most distinguished collaborators from Orsay, Michel Davier, someone who's worked here almost over the entire history of the laboratory. Andreas himself got his start with one of our competitors, the Aleph experiment at LEP, but in the mid-90s he came here and was one of the grounds-up collaborators in the Babar experiment. Also, during all of this time, one of the world's experts on the tau lepton, a subject very fond to us here. After Babar, Andreas went to CERN as a member of the ATLAS collaboration. He was a manager of this monumental project of data preparation for ATLAS, one of, with CMS, the world's largest and most complicated data streams. After that, he got involved in the search for the Higgs boson in gamma-gamma, a specialty of the Orsay laboratory, and also he is now the convener of the Supersymmetry searches group in ATLAS. So it's a very lofty position in the world of high-energy physics, and it's a good place to survey what the terrain is now and what will happen in the next 50 years. So let's welcome Andreas.
Thank you. Does this work? Does this work? Can you hear me? Yes. Thank you very much, Michael, for this introduction. I'm really excited, a bit nervous, and I'm very honored to be able to talk to you here about this very particular moment for SLAC and also for particle physics. Of course, as you know, the completion of the standard model, and a model to which SLAC has so decisive contributions throughout the many years. And so most particle physicists believe that it's all of us, everything is made out of a handful of particles and forces. And so we should really imagine the creativity of nature to create all this out of just particles and forces. And through its relation with cosmology, the study of particle physics is also, of course, a journey back in time. Now, mankind's search for the smallest unit of matter is in its different form, and the forces is much older than, of course, than particle physics itself. And particle physics is just a term for the search for the ultimate laws of nature. Now, I would like to show you, just quickly as an introduction, the scales of particle physics. And so unfortunately, I don't have a stick, so I will try to make big movements. And so if we look very big movements we need to get to this high energy here. And we see an anti-proportionality between energy and distance. So in order to resolve very small distance, we need a lot of energy. And throughout the time, we see here in 1900, we were able to resolve the atomic scale. At 1970, we were able to resolve the QCD scale. And now we are really fully resolving the electroweak scale with the Higgs boson, with electroweak symmetry breaking, and we hope then, of course, additional particles coming up. And if you just look at the pattern, there is a good reason to have additional particles coming up just beyond the electroweak symmetry breaking scale. And then we don't know what is happening. We have a few hints what should happen. For example, at very high energy, gravitation becomes strong, and so we expect certainly new physics to come in there. We expect also there's grand unification of the forces of the order of 10 to 16 GeV. But what we are now really concerned about is 10 to minus 10 seconds after the Big Bang, the TeV scale. So if we want to compare nanoscience, of course, very small, we have seen. And if we compare the TeV scale with nanoscience, we compare a flea with the size of the Earth. The standard model consists of 24 elementary matter particles and 3 forces, and a total of 26 parameters at least. It could be 28 including the neutrino masses here. We are organized in matter particles, organized in 3 generations of leptons and quarks. And then we have the force quanta, where we have the photon for the electromagnetic force, the W and Z bosons for the weak force, and the gluons for the strong force. And the electromagnetic and weak force are actually unified in an electroweak symmetry, an electroweak interaction. And at the vacuum, at our energy, this symmetry is broken by the Higgs particle, which also generates the boson and the fermion masses. And this is a very important particularity because of gauge invariance. In fact, gauge invariance is a very fundamental principle, a geometrical principle, which means the invariance under local space-time transformation, which is very important because from this principle we can derive all the forces in the Standard Model and even gravitation from this geometric principle. So we don't want to give it up. But in fact, there's a particularity in gauge invariance. It means that all the bosons and the fermions should be massless. And this certainly is not the case. So we need a trick to give them masses without breaking gauge invariance. And the trick is spontaneous symmetry breaking. This is something which nature has done already in other areas. For example, you look at superconductivity, for example, where the Cooper pairs in the superconducting phase give mass to a photon. So this is quite similar to the Higgs mechanism here. And so in order to break symmetry consistently, we need to introduce a new field, which is a doublet, in fact, a doublet complex field with 4 parameters. And we need a potential for this field. So the 4 parameters, if we use judiciously the potential, the 4 parameters will be eaten up by the masses of the W and the Z boson, and a single parameter is left, which is the so-called Higgs boson. And all this together is the Englert-Brut-Higgs-Guralnik-Hagen mechanism. We will short-term this Higgs mechanism. And so we should look back. In the early universe, we have very high energy. We are above the electroweak symmetry breaking scale. So electroweak interaction is unbroken. And we have a potential of this phi, which has a 0 value at the origin. So we don't have any breaking of the symmetry. Now the universe expands, it cools down, and we pass through the electroweak phase transition, which is actually very fast. Higgs percolates and bubbles, and then finally it comes up and builds a vacuum expectation value, so a non-negative value at the vacuum, at the zeroth energy. And the potential to describe this could be, for example, this term. It's the simplest term for a scalar potential of this type, with a mu square term, a lambda term to the order 4th, and then some term which gives the fermion masses. And this term has to be negative. This is an important feature, so this gives this feature here. Then lambda has to be positive, goes up here. And in fact, we want that, in the Standard Model, this term gives the mass of the Higgs, and this is directly then also described proportional to the mass. So if the mass is too large, lambda will be too strong. This is a self-interacting term. If the mass is too small, in fact, this potential might have another minimum and might be unstable. So this would be an unstable electroweak minimum. So this is very, very important feature. So we need these parameters have to have the right values. So now, a little bit more imaginative. We are again at the Big Bang. We're in the symmetric phase. No electroweak symmetry breaking. All particles are massless and travel with speed of light through the early soup. Now a Higgs field displaces the ground state, breaks gauge symmetry. It fills all space and time, but no orientation. It doesn't have any spin. And you see that's actually very fast what's happening here. But you see the particles start to interact with the condensed Higgs field. And the stronger the interactions, the slower they become, and the bigger is their mass. So this is the mass generation mechanism. And it's really the action of the Higgs field creates here a vacuum viscosity. OK, so to introduce this picture, massive particles interacting with the condensed Higgs field like fireflies in the night sky of Ochiai. This is a place close to Tokyo where you can see many, many fireflies. So the Higgs boson, is it the last of the particles? We actually did know quite a number of things already before it, and the only parameter which was not known was the mass. And all the couplings, everything else can be computed once we have the mass. And even on the mass from the, at that time, precision and intensity frontier, we already had quite interesting information, also delivered, of course, by the fantastic ALR measurement at, a symmetry measurement at, oh great. A symmetry measurement at the linear collider at SLAC, SLC. And so although these like lab also at CERN and the Tevatron could not produce the Higgs in particular lab, of course, and SLC could not produce the Higgs directly. They could, in fact, see the Higgs through the uncertainty relation, through virtual production of Higgs, which does change the actual cross-sections, the asymmetries, variables like also the W mass, which are measured. And so from a global fit of these data, it was possible to determine that the Higgs has to be lighter than 153 GeV. So that's, of course, a very interesting information. There's another reason. Look again at this potential we have here. And the mass determines really the form of the potential. So if the Higgs is too heavy, the Higgs self-interaction will become non-perturbative. This is something we do not like. If the Higgs is too light, the potential will not be stable. There will be another minimum showing up, and we might tunnel into this other minimum in our universe. And this is something we don't like either. And so these constraints become stronger and stronger if we go up in energy. And if we go up to the Planck scale, assuming the standard model is valid up to the Planck scale, then, in fact, we much steer a very narrow course between these two disastrous scenarios. So this was what he knew before July 4th. Since July 4th, we know much, much more. We have seen the Higgs. And to go this way, to achieve this goal, to be at this day, and to present these results was, of course, a very, very, very long endeavor, which started by a lab note by Lynn Evans and Schnell and on 83, brainstorming the idea to have proton collisions or proton-antiproton collisions in the lab ring. And then the first workshop was in 84, so almost 30 years ago. And so you assume what stability this needs and what incredible, what the people had to invest into this to make this possible. So producing the Higgs boson and searching for new physics at the TeV scale requires a huge machine. And we use the fact that looking deeper into matter, we need a lot of energy, a powerful microscope, discover new heavy particles. We use Einstein's relation between energy and mass and probe the conditions of the early universe. We use the relation between energy and the Boltzmann relation. And then we use the trick, which was introduced by Lawrence in the beginning of the 30s. That was a very, very small cyclotron. It became bigger with time. It became 27 kilometers huge, a proton-proton collider here. This is the LHC ring. This is part of the injection chain. Here is CERN. There's another side of CERN here. And so far, last year, we had a 7 TeV proton-proton collision. This year, we had 8 TeV proton-proton collision. Luminosities in the detectors of 5 inverse 10 to 1 last year. And now we have more than 10 inverse 10 to 1 this year. The results on the Higgs were made of the order of almost 6 inverse 10 to 1 on 8 TeV collisions this year. And so we have four experiments, 2 general purpose detectors, ATLAS and CMS, and then LHCb for dedicated B physics studies, flavor physics, and ALICE for dedicated heavy ion studies. I cannot go into the details of the detectors, but what we are looking at is proton-proton collisions. So we think protons, that's U and D quarks. That's how protons are made. And so this is the picture we have. But in reality, of course, it is much more complicated. It is really a complicated compound wave out of partons where we have all quarks and also gluons, and with different parton distribution functions. So corresponding to the momentum transfer of these proton-proton collisions you have different quarks and different partons contributing to it. And the Higgs is actually very light compared to the center of mass energy we have. So in fact, we are dominated by low x. We saw a low x parton distribution function, which are completely dominated by gluons. And so in fact, what we have is a gluon-gluon collider and not a proton-proton collider. Since the gluons don't interact directly with the Higgs because the Higgs couples to mass, we have a loop here through top loops. And in fact, we have already 200,000 Higgs on tape each experiment. That's a lot. And we think, why did we wait so long until showing that we have the Higgs? And in reality, it is, of course, very complicated because the large majority of these Higgs we can't see because they're completely drowned by backgrounds. So what we really look at for low mass Higgs is the channels 2 photons, the Z, where for Z we only look into 4 leptons, so each Z goes to 2 leptons, and the W, where each W goes to a lepton and a neutrino. And this photon in particular is a very, very small channel, very, very low branch fraction, but it's very pure. So we were able to see this in our detector quite nicely. So I can show you a picture of the CMS detector here. You see the 2 photons. This is a Higgs candidate. We don't know whether it's a Higgs. There's a lot of background for a given event. We can never say that's a Higgs in this case here. So that's a Higgs candidate. What we do is we compute the energies here. We measure the energies. We measure the angle and compute the invariant mass from this. We plot the invariant mass and look for bumps. And you see here, ATLAS has seen a bump here at around 126 GeV. CMS also has seen a bump here, around 125 GeV, and very good agreement. Both see, in fact, more than a 4 sigma deviation from the background-only hypothesis in this channel. We can also look into ZZ production. So in Z, every Z can go to 2 leptons with actually a small Brownian fraction of 3% only. So we can have 4 muons, 4 electrons, or 2 muons and 2 electrons. In the event, in this case, is an event in CMS where we have 2 electrons here and 2 muons. The muons are minimum ionizing particles. They penetrate the full detector. And so we can also, again, we compute the invariant mass of these particles and plot them. And we see we have much less background here. That's nice. It's a very pure channel. And we have a peak. That's the Z. It's not the Higgs. And also the Z can actually go to 4 leptons. We have a small deviation here in both experiments, actually. This gives us an excess of 3.6 sigma in Atlas and 3.2 sigma in CMS, again at the same mass as we had for gamma-gamma. Then finally, we have the mode in 2 leptons, in 2 Ws, where we have neutrinos. We cannot reconstruct the neutrinos. We can only reconstruct the transverse energy balance of these neutrinos. So we can do something like a transverse mass, so something like an invariant mass, which is not as good. It doesn't have very good resolution. You see in red here the resolution of this mass to a Higgs. But we can make a counting experiment. We can see if we have an excess of events. And we do have an excess in Atlas, and we do also have a small excess in CMS, 2.8 sigma in Atlas, 1.6 sigma in CMS. Now we can put all this together, and we can ask ourselves for each mass we have, what is the probability to observe what we've seen if there's no Higgs? So then we see the probability is quite high everywhere but here. And so we have here a deviation of 5.9 sigma in Atlas and 5 sigma in CMS at a mass which is compatible. So clearly this is the observation of a new boson, a new particle. And the mass of this is of the order 125.7 plus or minus 0.4. This is a poor man's average here, but it is probably pretty much that. So the mass is actually already very well known. We just discovered it and already know the mass very well. OK, so there was a huge press coverage. I went the next day, of course, I went to the kiosk into the news shop to look, and every journal had the Higgs discovery on its first page. This is really a rare moment for particle physics, so we are really happy to have that. Now, also Tevatron, of course, has many years of excellent Higgs searches, and many ideas were brought into the LHC experiment. Actually, also many ideas from the Babar experiment here at SLAC were brought into the LHC experiment. We reused lots of the fitting tools, of the way to do analysis as it was done in a very dramatically modern way as it was done in Babar. We do it also for Higgs searches. And so Tevatron has also an excess, which is in the BB channel, Higgs to BB bar, which is very hard for the LHC. So it's very nice to have this of approximately 3 sigma, a little bit less here at the actual Higgs energy. Now, the Atlas and CMS experiment also, of course, right away start to look into the actual. So you compare each channel with the standard model prediction. And so the signal strength would be 1 in this case. This is the standard model prediction. And you see that Atlas in these 3 channels, the most important channels, is a little bit above. CMS also is compatible with 1 here. And both experiments have a little bit of an excess in gamma-gamma, which excites a lot of theorists, of course. But we have to wait a long time until a bit more, not a long time, actually, a bit more to see where this is going to. And I would like to cite here, there was the Higgs hunting workshop just after ICHEP, and this is, of course, a great opportunity to discuss all these results. And Michael Peskin was actually giving the theoretical summary talk, a very nice talk. And I would like to cite this here, what he said. The standard model strength, the Higgs coupling to WW and ZZ, is prima facie evidence that the particle is a CP-even spin-zero state from a field with a vacuum expectation value that breaks SU2 and U1. And this is really a subtle comment, because the strength indeed to WW and ZZ is normally, this would be a higher dimension operator, and it would not couple if it didn't have a vacuum expectation value. So the fact that we do see this is really indeed not only showing us we have a new particle, but also showing that it breaks electroweak symmetry, which is really interesting. So a new era in particle physics has begun, and the exploration of planet Higgs is starting. So we have many questions. We want to really precisely measure its mass with the spin, of course. Does it break electroweak symmetry? How does it couple to the standard model particles? Does it couple to new particles? Really interesting. Does it have any invisible decays? Does it have brothers and sisters? It could not be just a minimal Higgs scenario, but more Higgses. Does it have distant cousins from higher symmetries, for example? Is it a natural scalar? I will come back to this natural question. Now, we can go back, we can compare to what we knew before, and we see we have a fantastic agreement, of course, with the prediction of a like Higgs from the intensity and precision frontier. And we can back also to this plot, and we see actually the Higgs is just sitting at the metastability border. And that's quite interesting. I think many theorists are thinking about this. This means the Higgs self-coupling at the Planck scale, if we only have the standard model, is very weak, very, very weak. And that's interesting. It probably has consequences. But this is only true if the standard model doesn't have additional extensions in the TeV scale. So the discovery of the Higgs boson completes the standard model, and it's a triumph for the imagination and rigor of the human mind. And it's a triumph also for the greatest experimental endeavor ever, the frontier of accelerator and detector technologies, global data sharing and analysis, and global collaboration. Now, the standard model holds tight. I would like to give you a few examples only. I had lots of them, but then I had to cut down my talk, so I had to stop. So I'll show you only very, very few. So we have here, this is a picture of electroweak unification once again. So we can actually predict from electroweak theory, knowing the Higgs mass and knowing a few other parameters, the top mass and the W mass. And you see now with the Higgs, we have a very precise prediction here. Compare this to measurement and are in very good agreement. So this really is the proof of electroweak unification. And there's a crucial contribution, of course. One of the far most important measurements stem from SLC, from SLAC. Now, this picture I have to show. I mean, I can't come here and not show this picture. So there is, we have three generations. Three generations allow us matter-antimatter symmetry violation. We must have matter-antimatter symmetry violation to create the matter universe we think we live in. So that's absolutely important. And the standard model does provide this. It doesn't probably provide enough, but it does provide the feature of matter-antimatter symmetry violation. There's a single parameter for this. And it actually gives rise to a huge amount of different phenomena which one can measure. And there, judicious people have built an accelerator which can measure this with unprecedented precision, which is this blue thing here, sin to beta, but also all the other measurements. And all the measurements come together to a single point, which was, of course, the confirmation that indeed the CKM phase, this CP violating phase, is the primary contributor to CP violation in the standard model. And it gave rise to a Nobel Prize for Kobayashi Maskawa in 2008. And certainly, this successful program has relied completely on the strong vision and leadership of SLAC to build the PEP2 B factory and also Babar. This went together, of course, with the corresponding experiment, which was running at very successfully as well at Japan. So the standard model holds tight. That's wonderful, because we quantitatively understand what we see, and we can exploit this understanding to look for deviations. Now, I would like to show one example of a deviation, which is a very small deviation. For example, the anomalous magnetic moment is normally the magnetic moment of a muon or an electron is 2. We know this from the Dirac equation. Then through Heisenberg, once again Heisenberg, we get a small offset of this, which we can predict to parts per million in the standard model, an incredible precision. And we can measure this also to parts per million. A fantastic experiment at BNL measured this. And we see since about 10 years we live with this deviation between 3 and 4 sigma. It's calculated by several groups, and they all find similar results. And so this is, of course, interesting to follow up. Then there is another feature I wanted to mention in the standard model, which is actually we should have CP violation in strong interactions. That's something people tend to forget, but we should have. We don't have. It should give rise to an electric dipole moment of neutrons. And we never see this. So we have actually very, very precise measurements here, smaller than 3 × 10⁻26 centimeters neutron electric dipole moment measurements, which give rise to the CP violating parameter being smaller than 10⁻10. That's completely ridiculous if there isn't any mechanism which makes it so small. And so this mechanism could be a new symmetry, which is the so-called Peccei-Quinn U1 symmetry, which gives rise to a new pseudo-Nambu-Goldstone boson, a new particle, which actually has the nice feature that it condenses in the universe, and could be, although it's very, very light, it could give rise to the cold dark matter we have. So we have two reasons to search for accidents. It's something, I think, which is very, very important. And finally, I must mention, of course, the neutrino revolution. Since 15 years, we are used to, at every conference, we get new, very interesting results from the neutrino sector. And now we know lots of things. We know they're very, very, very light, much lighter than the rest of the fermions and bosons in the standard model. We don't quite know what the mass hierarchy is. We know they're lighter than of the order of an electron volt. And now we also know their angles. So there are 3 angles. It's just like in the CKM matrix, and all 3 have been measured now. In fact, the hardest one, θ13, is now better known than the supposed to be less harder one. And, but this is for the moment what we know, not more. And so there are many, many questions. We want to understand the absolute mass scale of neutrinos. We want to see whether we have a normal or an inverted mass hierarchy. We want to measure, of course, CP violation in neutrino oscillations. We want to measure the unitarity of the neutrino mixing matter. So the same program as we did for the SLAC B factory. Neutrinoless double beta decay to understand whether neutrinos are their own particles, antiparticles, or whether they are direct particles. And whether there's any existence of sterile neutrinos, neutrinos which do not obey weak interaction but only gravitation. So can we conclude from that the standard model is the theory of matter from what we know so far? And certainly we cannot. There's no way it could be. The Higgs is the only fundamental scalar. All other scalars we have are composite particles. So it's very strange to have a single fundamental scalar. There's a huge mass hierarchy between the matter particles, a gauge hierarchy problem. I will come back to this problem in particular. There's dark matter and dark energy, of course, not contained in the standard model. There's inflation, also not contained. The matter-antimatter symmetry, the CKM mechanism is 9 orders of magnitude too small to create the matter-antimatter symmetry we observe in the universe. Grand unification of the forces is not generated by the standard model. The strong CP problem, I've said, massive neutrinos, and finally gravitation. Gravitation is not at all included in the standard model. We cannot be happy with such a model at the moment. So I will come back to these ones because these problems here are directly related to the potential I've shown you already from the Higgs. So this is the Higgs potential. And actually, I liked also Michael's reaction at the Higgs hunting workshop. In some way, this exemplifies our successful description, but lack of understanding. Is this what we just postulate, the potential we want, or shouldn't we actually have a better theory which predicts this potential? It comes out of dynamic properties of this model that the potential has this form or another form. So first, the mass term has a huge problem. In fact, it receives radiative corrections of this type with top exchange, for example. And if you go up in energy and you cut off the standard model, for example, at ground unification or the Planck scale, at the Planck scale, the mass of the Higgs would actually have these corrections become huge. And the mass of the Higgs would have the mass of the Planck scale. And so to have the Higgs mass so low means we need to have a cancellation, a ridiculous cancellation of 2 numbers of 10 to 19 GeV to come up with 100 GeV. It is completely impossible. That cannot be the truth. So then, of course, we have to understand the lambda, whether we are in a stable or in a metastable universe. We have the same flavor problem. These couplings here give the fermion masses, but they're very, very different. And we have no way in the standard model to understand where the hierarchy stems from. And then also, is this actually the right potential? And if the Higgs field indeed fills all space-time, is it related to inflation and dark energy? That's an interesting question. So getting back to this here, the missing protection of the scalar potential to high-scale physics, there's no symmetry if we put the Higgs mass to 0. If we put the quark masses to 0, for example, we recover chiral symmetry, which is very interesting, which just naturally makes the quark masses light. It's not the case for the Higgs. And so the Higgs is considered the portal to new physics. So the Higgs discovery now, of course, puts these questions into the spotlight. And theorists are incredibly creative in producing models which could evade these problems. In particular, for example, weakly coupled solutions like supersymmetry, composite Higgs, which are more strongly coupled solutions. And all these, of course, introduce new physics at the TeV scale, extra dimensions, for example. So, for example, does the symmetry between fermions and bosons regularize the Higgs radiative correction? So we have seen this correction here, if you have a top loop, produces a huge contribution to the Higgs mass. And then if we had the corresponding scalar loop here, it gives a negative sign and cancels to all orders of perturbation theory this contribution. That's very, very elegant. It's so elegant that it must be true. We have to see. So that's weak scale supersymmetry, and we can imagine this in our case. So Mr. Higgs wants to fall into the scalar precipice, which is incredibly deep. And Mrs. Susie is sitting here and holding it back at the electroweak scale. Now, the Atlassian experiment have a huge amount of production, very, very productive in searching for all these new physics models. All these physics models don't only produce Higgs partners, they also produce lots of new particles which can be strongly interacting, for example. These are all the limits in supersymmetry. These are all the limits in Atlas for models beyond supersymmetry. And you see we are reaching the TeV scale in these models. So clearly the LHC is pushing the limits on new phenomena here. Now, and I have to go to the next 50 years. So remember particle physics 50 years ago, there was no quarks, no CP violation, no standard model. There was I mean, all these things is basically impossible, no Higgs mechanism. It's impossible to predict what is going to happen 50 years from now. So I just want to go along a little bit the options we have. So we have the famous option of the energy frontier, the intensity frontier, through other areas I would like to mention, and then also the cosmic frontier, which will be covered greatly by Jonathan Feng and Renée Ong later. And the introduction to future accelerators, I will assume you know what these accelerators are, and so then Frank will really put the details on these machines later today. So the high energy frontier, all we're doing will depend on what the LHC brings us. So far we have a new particle which we have to study for sure, it's clear. But then the next, of course, depends on whether we find additional particles. So the options we have for this is we can double, or even more than double, the energy of the LHC by putting larger, stronger magnets into the ring. We can build a Higgs factory, which would be a linear collider, E plus E minus, colliding to 500 GeV, or even having the possibility to go to 1 TeV. This is a mature technology. We could basically start the construction right away. And then there is CLIC, which allows to go to much higher energy, but it's new technologies, which needs a little bit more R&D to be able to run it. And then there are very interesting additional projects, like a very large LHC, which needs, of course, a new tunnel. That's a big investment. Then LEP3, which has the idea that's a relatively new project, which reuses the LHC tunnel to build there a stronger E plus E minus collider than LEP to be able to produce actually Higgs Strahlung, so Higgs plus Z. And then there is the very fascinating idea of a muon collider, which is new everything. It is very, very challenging technology, but of course it has extremely interesting advantages because it's very, very compact and was supposed to be much cheaper than these huge solutions here. So I would like to make one point here. CLIC and muon colliders are basically here representatives of new accelerator technologies, and there are very powerful alternatives which are actively developed at SLAC. And I would really like to mention these very, very interesting high gradient accelerators, for example, any kind of wake field acceleration like plasma wake field acceleration. And there was a very interesting talk last year from Thor Raubenheimer at EPS-HEP on this, and Frank will, of course, also go into the details of these possibilities, which are very, very fascinating. So let's assume we have observed lots of new physics at the LHC. We have the option to build everything. We want to build an ILC to measure the Higgs, CLIC to measure with precision the heavy particles, and also a high energy LHC to go beyond what we've seen so far. That's basically an easy scenario. If we only find the standard, so we stay with the standard model Higgs so far at the LHC, we don't observe any new phenomena at the LHC. In that case, we still need an E plus E minus collider to measure to great precision the Higgs properties. And then if we do not observe any new physics beyond the Higgs at the LHC, but we do observe physics at the intensity frontier, new physics, for example, charge lepton flavor violation. In that case, we need to estimate what is the scale of this new physics, and we would need a new high energy collider to find this new physics. And we also need an ILC, a Higgs factory, or a LEP3, to be able to measure precisely the Higgs properties. So in any case, in either scenario, in 50 years, we should have built, operated, and exploited a new E plus E minus collider. So what will have taught us and the LHC together, of course? The Higgs couplings here will have been measured to % accuracy. We also need theory improvements here to be able to really exploit this fully. New heavy particles may couple to the Higgs and modify these couplings. An interesting scenario, of course. We have to measure the self-coupling of the Higgs, so the Higgs coupling going into two Higgses. This gives us a factor of 1,000 reduction in cross-section in the LHC. It's a very hard measurement. We need a lot of statistics for this. But of course, this gives us directly access to the measurement of the Higgs potential. It's absolutely crucial to do this measurement. So if new particles were discovered at the TeV scale, they will have been studied in detail at the TeV linear collider, and energies up to 10 TeV may already have been covered by the high energy LHC in 50 years from now. We will have learned and understood if the Higgs is fundamental, regularized by new weak couplings, for example, supersymmetry, or other composite, we have an additional symmetry at the TeV scale, for example, and the Higgs is then some kind of a pseudo-Nambu-Goldstone boson. This, in any case, will be a revolution to our perception of matter and force. Now, if no new physics is discovered, the hierarchy problem may be reality and naturalness as a scientific criterion has to be questioned. In this case, a revolution of thinking physics and possibly a hint to statistical choice of the universe's parameters. Now, we also have to think about what will happen if we find new physics to all these beyond the standard models. And this is a picture of Hitoshi Murayama, who was who has put together the various models. And of course, if we do see them, their nature will have been determined at a linear collider. Dark matter candidates may have been found and completely solved the dark matter puzzle we currently have in the universe. New CP violating interaction, so matter-antimatter violating interaction, would impact our understanding of baryogenesis, so the creation of matter in the universe. And likely the new physics will have taught us about the physics at energy scale far above any accelerators. Then I would like to briefly mention also, of course, very important, the intensity frontier. Through Heisenberg's uncertainty relation, we can create particles which are much heavier than those we can directly create in our accelerators, and we must exploit this. And wise research sessions will have allowed to exploit a huge physics potential of this high intensity frontier. Now, new techniques for the measurement of electric dipole moments of neutrons, electrons, and muons will have improved the current sensitivity by 3 orders of magnitude. That's absolutely astonishing and a real thing which can show us new physics in this area. The LHC and new B factories will lead to sub-percent CP violating and rare decay measurements. High-intensity proton drivers, more than 5 megawatt proton source, will create a huge amount of kaons and muons to be able to study rare decays. For example, we can measure, that's really interesting, for mu to E conversion, the charge lepton flavor violation, which is forbidden by extremely small in the standard model, not observably, to 10 to minus 19 with the absolutely true potential for discovery here. And also we can see, for example, this golden decay of k long to pi by 0 nanobar with a 10 to minus 11 branch infraction. Of course, the linear collider will also then improve our precision. We can redo the electroweak fit and get lots of information about this. Then, of course, the part of the intensity frontier is the neutrinos properties. And Fermilab has a very nice program going through the various steps and ending up with a neutrino factory, and then even going to a muon collider. That's really a very interesting program. And the combination of long and short baseline and reactor neutrino experiments will have established the neutrino mass hierarchy, precision angle measurements, and hints on leptonic CP violation. These will be systematically limited, so certainly the way to go is a neutrino factory, is a logical next step, and maybe in 50 years, I hope, is already done. Ton-scale neutrinos as double beta decays will have explored the nature of neutrinos, so whether it's its own antiparticle or not. This is crucial to know whether we can use neutrinos to create leptogenesis, and through leptogenesis, through interesting processes, produce baryogenesis. This is a very, very important thing, and for this we need to know whether neutrinos are Majorana particles or not, so their own antiparticles or not. And we have also information on direct neutrino mass measurements. We will go up to milli-electron volt for these masses. Finally, megaton neutrino detectors will have achieved a proton lifetime sensitivity larger than 10 to 36 years. Currently, we are from Superkamiokande in Japan, 2 times 30, 10 to 34, impacting our understanding on grand unification. This is something I really want to emphasize. The fact that charges are quantized in protons, so proton is the same charge as the electrons, or quark has 1/3 of the charge of the electron, must mean that there is grand unification of electroweak and strong interactions. So we have to observe proton decay to be able to really, proton decay is a messenger of this grand unification. It's extremely important. Finally, axion experiments will have covered the cold dark matter range between 1 microelectron volt and 1 millielectron volt. This is the most interesting range for axion to be able to be a cold dark matter candidate. And then there will be many, many experiments on direct detection of dark matter in space and on Earth, which will be discovered by Jonathan Fang later. Finally, the last point I have to mention, of course, theory. The last 40 years, we have seen a profusion of theoretical ideas motivated by the shortcomings of the standard model, by cosmological observations, and by the Planck scale physics. Experiment is behind, far behind, but absolutely needed to understand the choices nature took. I have told you, supersymmetry is so elegant, it must be true. It could be that nature didn't choose it. So the next 50 years shall be the age of experiment and theoretical truth. And I would like to point out also that particle theory is more than just model building. It is also hard calculus and programming on which the interpretation of the data crucially relies. We cannot exploit, for example, the LHC without all the work the theorists have done to do our predictions. There was a very, very nice talk by Lance Dixon on the NLO, next to leading order QCD revolution at ICHEP, which you should look at. And of course, similar to experiment, it requires large-scale resources and organization. So theory in this way is getting more and more into also big organization, which is necessary to be able to do these calculations. So this is, for example, a proton-proton collision, which you really have to calculate. Theoretical revolutions are perhaps even less predictable than experimental one. It's clear, however, that SLAC must remain a world-leading theoretical center. And although particle physics started by looking at the sky, at cosmic rays, and we get many, many ideas from cosmology and astrophysics, in the end, particle physics has to rely on accelerators. And if you look back at the discoveries which were done, so this is for all the particles of the standard model, in particular SLAC contributed the U and D quarks, the charm quarks, and the tau with these eminent Nobel Prizes from there. And you see a nice asymmetry, which Yong-Ki Kim also pointed out, between the material-oriented US and the interaction-oriented Europe. Certainly, each new accelerator project pushed the limits of technology and organization and ended enriching our understanding of what we are made of. It's the price of knowledge. There's absolutely no other way to get there. So if we want to try to build a landscape of particle physics labs in 2062, I'm going far too much what I actually should do, because I really have my nose in the data. But if we do this, we have an extremely challenging experimental program which requires global organization. We have several successful examples of global head organization like ICFA, the global design effort, also the Neutrino factory efforts, and also in communication we have interactions.org. I'm sure every particle physicist is subscribed to this very important source of information. And then the wonderful SLAC FNAL Symmetry magazine. And so we will have in 2064 probably or hopefully global labs in all the different world regions hosting the very large facilities. For example, Intensity Frontier at FNAL, at CERN, the Energy Frontier, at Japan, a new site, the Precision Frontier plus or minus, for example. It could, all the labs currently have various programs, so it could be the other way around. But this would be the best form of organization to have in every region a huge lab which could make these facilities. And then we need strong and versatile national labs with technological leadership that coordinate the research and development for new machines and detectors. And faceted SLAC is a very, very nice example of this, of course. So I will finalize here. The next 50 years, if we look back to what we've learned during the last 50 years, if we continue our path of globalizing our strengths and keep fruitful competition and the individual's creativity vivacious, we will keep up the pace to unravel nature's deepest mystery. And in 50 years from now, there will be new particle physics. We will have emerged with new symmetries, new particles, new interactions that have extended the standard model to a far more complete theory. And SLAC, in 50 years, will look back and enjoy its strong fingerprints on the making of it, as it does now on the making of the standard model. And I would like to congratulate SLAC for this achievement. Thank you.
So we have time for a few questions. Please wait for the microphone. Steve?
Most of the public presentations on July 4th and following referred to this as the discovery of a Higgs-like boson. You repeatedly referred to it as the discovery of the Higgs boson. Is there reason for your lack of caution?
No, I think it is true. We should be prudent. So far, we have a boson which has, within the large uncertainties we have, all the properties it must have to be a real Higgs boson. So that's everything we can say for the moment.
Earlier in your talk, you likened the Higgs mechanism to superconductivity. Could you expand on that a little bit?
Is there a theorist who could maybe do this?
Oh. If you turn this on. Mathematically, the Meissner effect in superconductivity is the same thing as what we call the Higgs mechanism in elementary particle physics. I can expand on that offline if you like, but that's the connection.
Yeah, it's called the Anderson-Higgs mechanism. And it's really, I mean, the original idea of the spontaneous symmetry-breaking really from Nambu also came from superconductivity through the creation of the Cooper pairs. Yeah.
One minute. Michael.
I wonder if you could show again the Tevatron data. It sort of was in a flash, and I couldn't really see the evidence there. Maybe you should discuss it also a bit.
So this is a subtracted plot, which you see here. So all contributions from background are subtracted. This is the dijet mass. So you look into the creation of a Higgs to BB bar plus association of a W or a Z. In this case, I think it's a W. And you plot the invariant mass of the BB. And you subtract all the backgrounds apart from WZ and ZZ. And so there is a little excess here in this area. But what actually is done at the end is a full multivariate analysis which creates. So this is just a projection of all the information which goes in there. But the real result is a full multivariate analysis which has a stronger discrimination than this one, than just the mass. So it's really very difficult to conclude from this on the actual power the Tevatron analysis has. It is much more than only this plot.
Okay, one last question.
Just a small comment with respect to this question over here. I noticed the Atlas paper has the word Higgs in the title.
Sorry?
The Atlas paper has the word Higgs in the title.
Yes.
The Atlas paper is very careful. It is a new boson discovered in the search for the Higgs boson.
Yes, exactly.
Yes, exactly. Very carefully phrased.
Okay. Andreas, thank you very much.